Okay, so now we have the second best student paper talk, which is given by Randy Lean. We're waiting for the vision.
Okay. There we go.
Very good. So Randy Lean, he will tell us that MIPco is equal to coRE.
Thank you for the introduction, and thanks for being here. So in order to really start this story, I want to first talk about a result that was done 6 years ago, which is a result called MIP circles RE, which is proven by G, Natarajan, Vidick, Wright, and andYuen back in 2020. And the reason why this result is really exciting, not only to the complexity community, is because it is related to a bunch of questions in both quantum mechanics and operator algebra. And one of the questions proposed in the MIP circle RE result is about the complexity of this MIPco class, which I'll introduce later, which the intuition behind MIPco really rooted from these connections to the quantum mechanics and operator algebra. And as you can tell from the title of this talk, we resolved this problem in this paper. So to really explain what an MIP or MIPco is, we need to first go over something called an interactive proof system. So interactive proof system is done between a polynomial time verifier and a computationally unbounded but untrusted provers. So in this case, the verifiers can generate multiple challenges and send it to the prover. So the prover is always trying to deceive the verifier by convincing the instance is true, even though it might not be. And we say the language L is in IP if for every yes instance, the verifier can come up with some behavior such that the prover can always convince the verifier to accept with probability 1, and whether in a false instance, the verifier can be convinced with probably at most 1/2. It turns out we know the complexity of this. This is equal to P space by result back in the 90s. Okay, so the first question is, how do we generalize this? Well, one of the natural generalization is something called the multiple interactive proof systems, where now the verifier gets access to potentially polynomial number of provers and can do multiple rounds of interaction. So now you might be wondering, why would having these multiple prover help? Well, it turns out you can kind of restrict it to the point where the provers cannot really talk to each other. And this gives the verifier the power of cross-referencing, meaning if the verifier asks the prover the same question and they kind of give different answers, then it looks really suspicious on the prover's side, and the verifier can just choose to reject it instead. So we also know the power of this. With this, the verifier can start verifying problem that's in any XP, whereas the exponential variant of the NP. So now I work on quantum information. First generalization, this is what happens if we add quantum entanglement between the provers. So for those of you not familiar with quantum entanglements, you should really think of this as the extra power that the prover gets. They still cannot really communicate each other, but they can win certain scenarios with higher probability. In fact, this was actually shown by John Bell back in the 60s that there exists some scenario that the verifier can design so that they can convince the verifier, so the prover can convince the verifier of a higher probability if they have entanglement versus if they don't have entanglement. In fact, the reason why John Bell think of this is about testing entanglement between our universe of having entanglement and having no entanglements, which happens to have the same structure as a MIP model. So to define this more formally, it turns out this is actually not really a good axiom to define quantum mechanics. So the most commonly used is actually something called the tensor product model of entanglement. In this case, entanglement is described between a tensor product between two Hilbert spaces, HA and HB, where HA and HB intuitively corresponding to the workspace that the prover 1 and prover 2 can perform. And I'll use MIP star to denote the complexity class described by one of these interactive proof systems where the provers gets access to this tensor product model of entanglement. So before I kind of go into the punchline where MIP star is, I want to just first point out that giving this prover extra power does not necessarily make the verifier more or less powerful. Because of the fact that provers can have a little bit more powers, he can actually convince the verifier some instance that can be true where it really should not be. But the verifier can also take advantage of the fact that the prover have this extra power to design specific scenario for the prover to actually take advantage of this extra resource they have. And if you really want to think about it, if we give the prover the power to talk to each other, then the verifier cannot really cross-reference each other with this cross-referencing string, and we really just have one prover interacting, and hence we have IP instead. Hence, it's actually really surprising the fact that when you're giving this prover this tensor product model entanglement, the verifier can all of a sudden verify the halting problem, or any problem in RE, which is a problem that's described complete with respect to the halting problem. Okay, so that's MIP star. So another variant, as I said, there's not really a single way to really define entanglement in this model. Another axiom that people consider is something called the commuting operand model entanglement. In this case, the prover the entanglement is described by a single Hilbert space, but the only restriction is that the prover's measurements commute with each other. So for those of you who work on quantum, the intuition corresponds to the fact that it doesn't really matter if prover 1 makes a measurement first or the prover 2 makes a measurement first. The outcome will be the same, and hence their measurement observer will commute with each other. And in fact, this is actually a more general notion of entanglement than the previous known tensor product model entanglement. And as a core of the MIP circle's RE theorem, that there actually exists some scenarios that the verifier can design so that the prover can convince the verifier with higher probability, giving this commuting operand model entanglement in comparison to the tensor product entanglement. So this is even like more power in comparison to the tensor product entanglement. However, the power of this only can be realized if the underlying Hilbert space is infinite dimensional. So an open problem is that the complexity of MIPco, as previously mentioned, is unknown. So as suggested by this talk, the main contribution is showing that the complexity of MIPco is actually coRE complete, meaning that this actually equivalent to the set of language which is complete with respect to the non-halting problem. So just give a little bit of visual perspective. When you take the intersection between RE and coRE, you get a set of computable problems. So MIPco is really also uncomputable, but in a really different sense. And just a special footnote, the co-modifier in this MIPco is a coRE, actually stands for different things. The MIPco stands for the commuting operand model entanglement, and the coRE stands for the complement of the language. You can thank whichever MIP star author who came up with this for this confusing notation. So just a special note, the fact that this MIPco is actually coRE complete is not entirely surprising. We know that previously that MIPco is actually inside coRE by the well-known NPA hierarchy. So the main contribution of this work is really by putting MIPco, by putting coRE inside a MIP protocol with 2 provers, 1 round, with completeness 1 and soundness 1/2. So the next one I want to talk about at least just how do we actually prove the RE/coRE completeness. This is something I call a compression paradigm, which is invented in this work. So in order to actually introduce this compression paradigm, I've introduced something called a uniform problem instance. So imagine a language L, which is infinite in size. A uniform problem instance is a Turing machine that takes the input of some integer I, and output each instance xi, and it runs in some uniform fi time. Intuitively, you should really think about this xi this Turing machine as a uniform way to generate a sequence of challenges for the language L, where the xi could either be inside the language or not inside the language. So a language is known as compressible if there exists this compression algorithm right here. So the compression algorithm takes the input, a description of a Turing machine, which is a uniform problem instance, and outputs another compressed version, which runs in Pauli logarithm time, whereas the original one runs in Pauli I time. So there's like 2 restrictions to it being compressible, meaning, first of all, the runtime of this compression algorithm must only depend on the size of the input Turing machine and independent of I. And also, in this case, the output of xi and xi compressed from the compressed machine could be different, but you're guaranteed that if the original machine, I've instance of the original machine is in the language, then the compressed variant, the I've compressed instance, is also in the language. And if the I've original instance from the original machine is not in the language, then the compressed variant is also not in the language. Okay. And the way you should intuitively figure out this compression paradigm is a compression inside the problem set generation. Because in this case, the xi and xi compressed could be like different machine, could be different instances, but you're guaranteed that this is either both inside the language or both not in the language, even after this compression algorithm. So one of the main results I show is that for any language L, if the language is inside RE, then it being RE complete is actually equivalent for it being compressible. And similarly, if L is inside coRE, then it being coRE complete is also equivalent to it being compressible. This is actually proven using some Keen's recursion trick that's based on the original MIP star equals RE theorem. And this could be like a new technique for showing a bunch of uncomputability problems outside of this MIP star MIPco model. So just to kind of emphasize a little bit more of this compression algorithm, this compression algorithm is actually language dependent. So if you feed it any Turing machine that runs in polynomial time and outputs some string, it will actually do the compression properly. And because of the fact that this compression algorithm runs time independent of I, this Pauli log compressed machine actually only gets access to the source code of this original Turing machine and cannot actually generate xi or decide xi itself. So this compression algorithm must be really proven by the property of the language. And as kind of proven, only like uncomputed problem can really define this compression algorithm. Okay, so now kind of going back to this MIP model. So in order to define a notion of this compressibility onto the MIP/MIPco model, we have to first figure out what the complexity is. And if you really stare at it carefully, the complexity kind of relies on the runtime of the verifier's behavior. So one thing that's actually the heavy thing that shows in this paper is that there exists a compression map which maps one of these uniform problem instances for a MIP/MIP protocol that runs in polytime. And it compresses to another instance which runs in polylog time, similar to this like uniform instance described earlier, such that if the original verifier had the behavior with the prover accepting with probably 1 for both MIP and MIP protocol, the compressed version will also have something that let's say MIP and MIP prover to convince you with probably 1. And similarly, the compression also preserves the soundness gap for the MIP/MIP protocol. So just a really special note, this compression map actually preserve the soundness and completeness gap for both the MIP and MIP protocols. But because we know MIP is inside RE because of a brute force search algorithm, this combined with the compression paradigm means that MIP is actually RE complete, recovering the result mentioned earlier. And because of the MIPco, it's inside coRE by this MPA hierarchy, it being compressible also means that it's coRE complete by the compression paradigm described earlier. So I'm not going to actually talk too much about this compression theorem. The only thing I'll say is that although this theorem looks really scary in picture, but in essence, it's actually a combination of 3 different techniques in a trench code. It being some very quantum technique known as self-testing, and a very more classical technique known as PCB by proximity. And just such a note, this compression protocol only works for a really specific set of MIP verified behavior, known as conditional linear sampleable. And in fact, most of these pieces are actually known in the original MIP RE paper. And the only difficulty is actually trying to get this working for the commuting operator model entanglement. And for this, you need a lot of heavy von-Neumann algebra theory, which I'll not explain here. So just a special note, similar to the MIT RE result, this paper also have a lot of implication between computability theory and operator algebra, and also quantum mechanics. And thank you for your attention. Yeah.
Are there any questions? Any comments? Yes.
I guess I'm curious about the operator algebras. Like, you didn't make them seem any less scary, and I was wondering if you recommend diving into those, or like what other applications they have. What about the operator algebras?
Could you repeat the question? Sorry, can you repeat the question? I can really.
Yeah, I guess are there other problems in operator algebras?
So the question is there any other problem in operator algebras? It turns out there's a very nice problem known as open question is like, does there exist a non-Sophic group? Where sophicity, roughly speaking, is can you approximate a certain group property by finite groups? And in fact, there is a complexity class called linMIP star, which is a variant of MIP star, such that if you show that this is uncomputable, you will show that there exists some sort of non-Sophic group out there.
Any more questions? Okay. If not, then let's thank actually all the recipients of the Best Paper, Best Students Awards again.